Um, so this video is not an answer key. It's more of kind of a mini lecture just on the notes that we've covered so far in Unit 3, going through the toolkits and sort of talking about what they mean. So if you've missed class or unsure what's going on in class or missed part of the toolkits and didn't quite get it, this is the video for you. So definite integrals, this is the beginning of the unit. So with Riemann sums. So a Riemann sum is a convenient way to approximate the area under a curve using rectangles. However, in order to get an exact area, an infinite number of rectangles is needed. Since we cannot algebraically evaluate the sum of infinitely many rectangles, we use a limit. The limit as a number of rectangles approaches infinity. Another way to express a limit such as this is with a definite integral shown below. Okay, so let me unpack that a little bit. So visually what's going on is, imagine we have a function. We sort of did this at the beginning of the year. We were trying to find the area under the curve. What we did was we drew these rectangles underneath and computed that area in order to sort of get what's called an approximation of what's under there. So this is a Riemann sum. Okay. And then we showed that with a sigma. This is a sum of many different rectangles. And they all had, if you remember, I'm going to keep it basic, but they also had a width. They all had a length or height. And they all had a beginning and they all had an end. This is just very basic. So this is old. This is what we did sort of the beginning of the year. And what we're transitioning to is, instead of these, it's what is called discrete, where it's individual rectangles that we can visualize. We're going infinite. So what that looks like is, instead of a bunch of physical rectangles that we can see, these rectangles are so incredibly thin, infinitely thin, that we are essentially just finding the entire area underneath the curve. And not an approximation. It's exact, or as close to exact as we can get. So that is where this is coming in. So this right here is, you can kind of think of this as the formal definition of an integral in a way, where it's written out in that summation notation. So what this is saying is, this is, if you can think of this is the beginning 0, and we're going to infinity. So we sort of have infinite many rectangles that are between B and A. This is their width. So this is basically, what this is really saying is infinitesimally thin is kind of what that's saying. And these are the heights. Okay. And instead of writing this with a sigma notation, we simply write it in integral notation, where, again, this A is the lower limit, and the B is the upper limit. And so visually, the way that integrals look is something like this, where you're going from an A to a B, and it's the area between them. That's the relationship. And then inside the integral, this right here, the f of x, this is called the integrand. This is the function. Like, so this right here, this would be the f of x. That's what we're looking at, or the function we're looking at. And then the dx, this is that width. That's that infinitesimally small width. So if you think about it, this dx kind of relates to that b minus a over n. And the f of x is this f of a plus b minus a over n times I. So this is sort of relating it to Riemann sums, but in reality, this is what we're using when we deal with integrals. This limit of a Riemann sum shown above represents the exact area under the graph of y equals f of x on a closed interval, a to b. each rectangle would have an infinitesimally small width represented as the limit as n approaches infinity of b minus a over n or dx. So that's saying what I just said, that these two things are the same thing. If you think about this, n is going to infinity, so this is just essentially zero, right? It doesn't matter what's on top. The bottom's infinity. It's like infinitely small, infinitesimally small. And the symbol, this is the sigma symbol, or sorry. This is the integral symbol. Integral symbol represents the S of summa, the German word for sum. So again, the sigma, right, terribly drawn, is similar to the integral, but they're not the same thing. This is discrete. This is dealing with things that we can touch. So like this is the sigma right here, and then this is the integral down below. Okay. Here we have an example of x squared plus 1. So this is just how that would be plugged into the Riemann sum notation. In the integral above, -2 is the lower bound, and 3 is the upper bound. So this is a would really be a -2, and the b would really be a 3. And the expression x squared plus 1 is the integrand. Okay. So this is, again, lower bound, upper bound, same as lower. You could say limit, upper limit. Definite intervals can also be used in functions with removable or jump discontinuities. Okay. So now we have on the back the properties of intervals. So this is what we were filling in. The first one is a zero interval. So that is the integral from a to a of f of x dx. So again, visually looking at what that might look like, you have some function, and you notice that a and a, this could be 1 and 1, 2 and 2. These are just a number. This is an a. It's just this. It's just this. There's this infinitesimally small rectangle, and that has an area of 0. So that's the first interval. Okay. Next is addition of intervals. So this is saying that if you have two integrals, let's say we have a, b, and c, then if I have the integral of a to b f of x dx, and I add the integral of b to c f of x dx, right? So I've got a to b, and I'm adding b to c. Then together, that's the same thing as the integral of a to c f of x dx. So if they're connected, right? If two integrals are connected, we can combine them to make one big integral. That's really what this is saying. Negation. So negation of intervals says that if we are instead going from b to a, let's say, of f of x dx, then I can switch these two values as long as I make them negative. So, you can use this as an example. What this is saying is that we're going from b to a. We're going in reverse. You're integrating in reverse. So since you're doing it kind of the opposite direction, the value is negative. So that's equal to the integral of a to b f of x dx. Okay. Multiplication by a constant is just integral a to b k f of x dx is equal to k integral a to b f of x dx. So essentially here, we can, if there is a constant inside of here, multiplied by the function, we can take that out front. And same thing. This is very helpful if you want to simplify integrals, just taking out a common factor and putting it out in front of the integral. We can do that. And this makes sense because sort of if you imagine like you had an integral like this, right? Imagine we had this interval that we were looking for, and I just doubled the function. So instead of, let's say it's at 1, now it's at 2, right? You can imagine that. Now it's this. Well, the function doubled, but also the area doubled. So that's what we're saying here. So if you double the function, if you factor the function by a number, same thing happens to the area. Some difference. This is if you have two different functions. F of x and g of x, and you're trying to find the interval of both of them, we can separate them out. So again, very useful for solving integrals. You want to simplify things, make things easier to deal with. We can write this as two separate integrals. So it'd be f of x dx plus integral a to b g of x dx. Makes it easier if we can separate them. Or maybe we want to combine them to make it easier. It will depend on the situation. And then lastly, translation. So what translation is saying, say you have an integral from a to b, and we were going to move it some c. Okay, of some f of x minus c dx. That is equal to the integral of a to b f of x dx. So let me explain what's going on here. So we know, we can imagine this on the right here. So we have some, again, I'll make up sort of an integral. Let's make it a little more specific. Let's say it's x squared. So it looks like this. And my bounds are like this, you can imagine. Okay, so this is, say this is a, and this is b. If I translate my interval, so instead of a and b, let's write a new one. Let's say I want to find it at this here and here. So this is a plus c and b plus c. So I just shift. You can imagine I just shifted those bounds over. And if I drew it the same, that would be a different area. You can imagine, right? But since, see here, this x minus c, when inside the parentheses of the function you subtract, you actually move that function to the right that many places. So what this does is it actually moves it to, imagine, like, it's not the best drawing in the world, but it's going to move my function the same amount that I move my interval. So again, this is important. This is when it's inside the parentheses. It's going to move to the right, that amount. So that's why these two are equal. You move the bounds, c, some number c, but you also move the function, some number c, to the right. So because of that, they're equal. Okay, so that was week 1, was focusing on that. Then we had, this is from Wednesday, after Thanksgiving. We have definite intervals. So we're still dealing with the definites. We still have these values, the upper bound and lower bound, but now they have variables. So definite integrals can be expressed on an interval a to x, where a is a constant. So it's good to label. This is a constant. So it's still an a, right? A to b. But instead of the b, instead of another constant, x is a variable. This type of definite integral results in a function called an antiderivative, which is often notated with an uppercase letter. So this right here, this f of x, this is the antiderivative. The antiderivative shown above can be interpreted as an area function that will determine the area under the graph y equals f of t from a to any value of x. F of x, capital F of x, or the antiderivative, can also be interpreted as an accumulation function, which computes an accumulated value of f from t equals a to any value of x. So this, the analogy that is helpful is to kind of think of this as like you're painting underneath a curve. So you have some a, you have that a that you begin with, and then you have sort of a shifting x. So the x is moving about. And so depending on how far I want x to be, then I can find that area. And that's what this gives me. Antiderivative of a function is a function capital F whose derivative little f is little f. That is, the derivative, so remember this means derivative, taking the derivative of the antiderivative equals little, the original function, essentially what this is saying. So, as an example, we'll make that clear. What is the antiderivative of f of x equals 2x plus 3? So this is where we learned our rule. We'll get to that in the next section, but what you want to ask yourself is the derivative of what gets you 2x? Well, that would be x squared, right? Because you bring the 2 down, subtract 1 would be 2x. And the derivative of what is 3? Well, that would be 3x, right? Because the derivative of 3x is 3. And then you have to add this c at the end. And that c represents a constant. Because I could add any number here. Because the derivative of a number or an integer is 0, it doesn't matter what I could add here. I'll always get this. So that's what the bottom explains. Since there are an infinite number of antiderivatives that are different only by a constant term called a family, we add a constant c to represent all of them. This is known as the general antiderivative or simply antiderivative. So that was 3.2. 3.3, or this is mislabeled 3.4, was now moving to indefinite integrals. Okay, indefinite integrals. Unlike definite integrals, which are defined between two bounds, indefinite integrals have no bounds and are written in the form. So you still have that integral symbol, still have that f of x, and you still have the dx, but you don't have any bounds. There's no a and b, no variables, no nothing. Okay. The indefinite integral represents all the antiderivatives. So this is f of x equals a 2x f of t dt. So remember, this is from the previous, what I just copied down there was that previous, this was what I copied down, these antiderivatives. It accounts for all the antiderivatives that are associated with every possible value of a. For that reason, an indefinite integral has infinitely many antiderivatives, each differing by a constant. So this is what I covered the last one, but it's so the integral from f of x dx is equal to that antiderivative plus the c. So the antiderivative of whatever this is plus that constant. So we could say integral of 3x squared plus 2x plus 5 dx equals x cubed plus x squared plus 5x plus c. So get this right here. This is that antiderivative of this, right? X cubed, take the derivative of 3x squared take the derivative of 2x, take the derivative of 5x, you get 5, and so on. And then that c is right here. Okay, fundamental theorem of calculus. So, if f is continuous on a to b, and the antiderivative is equal to a to x f of t dt, then the derivative of the antiderivative is the original function with x in it for all x from a to b. So what this says is that the derivative dx from some a, doesn't matter what the a is, to some x, f of t dt is equal to f of x. So essentially what it's saying, that these two things cancel each other out. Okay. Part 2. If f, capital F, is any antiderivative of little f of x, such that the derivative of the antiderivative equals the original for all x on an open interval containing a to b, then for this one, we say that the integral, this is for definite integrals, of a to b, f of x dx is equal to the antiderivative at b minus the antiderivative at a. And so this is what we practice a lot of in Fridays in part 2. Not so much part 1. Part 1 is about the exercise set, but part 2 is really what we focused on. Or an inverse power rule. So for polynomials with exponents besides -1, since we use a power rule to get our derivatives, we can do the inverse power rule to get our antiderivatives. This is the integral of, for the antiderivative of x to the power of n is equal to x to the power of n plus 1 over n plus 1 plus c. So really important rule to know, the inverse power rule. Okay, so we know we have the derivative version of this, but this is the integral version. Okay, let's do a practice. So when applying the fundamentals of calculus to evaluate a definite integral like a to b f of x dx, a common way to show your steps is the following. Okay, so we're gonna follow this as an example. So we have, I'm gonna write that out clearly. So we have the integral from 4 to 9, 2x plus 5 dx. The first step is to find the antiderivative. So I want to find the antiderivative of this in the middle. Okay, so let's do that. Using that inverse power rule, remember there's a little 1 right here, power of 1. So 1 plus 1 is 2, divided by 2 is just going to be regular x squared, plus, again, I mean, this is a common rule to know, is just that the integral of the antiderivative of any constant is just that constant times x. So it's just 5x plus c. Okay, and then from brackets over here, I'm going to do vertical line. You can do what you like from 4 to 9. Okay, that's step 1. Now step 2 is to find f of b minus f of a, the antiderivative of b minus the antiderivative of a. Now this is my b here, this is my a here. So we're going to do essentially f of 9 minus f of 4. Okay, so that becomes 9 squared plus 5 times 9 plus c, all in brackets, minus 4 squared plus 5 times 4 plus c. Okay, how I did that? I just plugged in 9 into it, then I plugged in the 4 into it. So let's see, this is 81 plus 45 plus c. That is 126 plus c, minus, this is 16 plus 20, 36 plus c. So this is 36 plus c. Then if I distribute a negative, what this comes down to is 126 plus c minus 36 minus c. Right, so I'm just distributing that to both of these here. And then if you kind of group the terms together, you get 126 minus 36, and you have c minus c. So I shifted them around a bit, and that will get me 90, and then these c's will cancel, so the solution is 90. And that is what we have covered so far.